Okay, today I'm going to talk about autoimmunity, three parts, as you see here. First, I want to talk about chronic stimulation. That leads to double negative cells of different kinds, different populations, and finally, where the tolerance occurs. First off, let me talk about the role of chronic stimulation. Every B cell is selected on self-antigens, as are T cells in the thymus. So positive selection, then negative selection. But positive selection is the critical thing. So if they don't see self in one way or the other, they won't survive. And the only thing they have to see is yourself, because we're not infected when B and T cells are being developed. So B cells in the bone marrow display an antigen receptor, and self antigens see those. And then T cells, same thing. And T cells, same thing in the thymus. They see self antigens. Or they actually see the TCR sees class 2 and then see APC. By the way, a B cell is an APC too. So this becomes relevant here. So the T cell and B cell see self antigens. And what happens is something very interesting. There's positive selection for self, and then negative selection. I remember a long time ago somebody said, "Why is it double whammy? You positive select yourself. No, so they clobber the ones that are self-reactive. But we selected on self-reactive at the beginning. That's just the way it is. There's a reason for it. It's easier to understand with the B cell because they anticipate what we're going to see. Maybe that's the way it's B cells anticipate we're going to see DNA or RNA in viruses, RNP, especially nuclear viruses. Here's the thing. Since they're selected on self, there's a different levels of selection here, that are good or bad. Probably, I'm going to say probably most people at this level are about the same. They all select on themselves. They know, if you look in the bone marrow, about half the cells are autoreactive. And probably in the thymus, nobody's been able to look, but we should get back to that. Probably half the cells are autoreactive there too, if you look at it. And by the way, this Meffrey was talking about autoreactivity is polyclonal. So that's something to keep in mind. The B cells react with polyclonal antigens. They don't recognize one thing, they recognize a lot of different antigens. And so the thing is here's what happens. They're chronic, but since they see self, they're going to, the most autoreactive ones, and even the other ones, are subject to this chronic stimulation, right? Because they're going to come out and they're going to see self. So what does it do? Chronic stimulation will do always the same thing. They'll activate. So that's why every cell is activated to begin with. They activate in the periphery. This could just be a different stage of dogged. Okay, so they're activated. This is the key concept. And then there's the ones that are overly activated at this point die. They get increased signaling. They die. This is the thing that's most easy to occur in a young B cell or a young T cell, but both cases. So we know transitional cells are very susceptible to cell death if they receive a self-antigen stimulation. So they activate, they die. Now what really happens is this thing called energy, aging, and senescence. So they die, but then they go along to get activated again. They die less, and somehow they die less. But what does happen is now that they become senescent. So what they do, the ones that don't die did something, right? They did something to not die, because they're autoreactive. So some just die, but some don't die. And what do? They start to, by the way, death is critical. So that's why apoptosis plays a role here. And other mechanisms of apoptosis, you have to think of that. Because this is so common. We know in T cells it plays a role. But in B cells, probably cell death plays a role. And as far as I know, we don't know what the mechanism for cell death is. But there's another thing that happens. And, the other thing is they downregulate the B cell receptor. As most people say, there's three levels. There's three levels. This is, there's the autoreactive T and B cell. They can either be deleted, they can be energized, or then they have this third thing that isn't really the case, where they can undergo endogenous light chain rearrangement. But let's just say they're either deleted or they're energy. Okay, energy. What is energy? Well, first off, what is deletion? That requires some mechanism, like fast. But what is energy? Energy then is just that they're going to downregulate a stimulatory molecule. So in the case of T cells, we know T cells come out of the thymus in the absence of fast. They come out of the thymus, and I believe they probably, the seeds in the periphery, you know, because we did it, thymectomy at 1 week of age, it requires the thymus, so they come out of the thymus, and they may express CD4 or CD8. And then they get activated, they can't die, so they downregulate CD4 and CD8. So a T cell becomes a double negative T cell. Very important concept, you know. So, and how do they do that? They go to the periphery and then they downregulate CD4 and CD8. They'll probably come out, they're activated, they don't have fast, and then they get activated many more times. So the T cell, the double negative T cell, is really a senescent T cell, probably. And whether they produce, you know, senescence of any cell leads to inflammatory cytokines. So they might produce IL-17, they might produce interferon gamma. You know, it's not clear what the double negative T cell. It doesn't matter. What happened is they came out and they didn't die and they're stimulated, chronically stimulated, and then they downregulate receptors, so they don't get stimulated as much. But then at the same time, that in that process of downregulating receptors, that requires activation. So maybe if you say, okay, they produce IL-17, you know, there must have been Th17 to begin with. They produce interferon gamma, they had that to begin with, CD8, for example. CD4s come out, they probably are turning into Th17. So that's the double negative T cell. Okay, for the B cell, for the B cell, the same thing. They come out of the thymus, or no, come out of the bone marrow, and then they die. They can die. Now we know that interferon is high, endogenous. Interferon is high. So that sort of prevents their cell, that promotes their survival and development. We have to think about that, because where does that come from? But we think probably it's right there in the bone marrow. It's an intrinsic property. But you know, nothing's intrinsic. You know, it has to be a reason for this. But they come to the bone marrow, they say survive or not. They start out with a better footing, but they do the same thing. It's interesting. So they're going to eventually come out and die. And this paper by, well, I won't go into it too much, but if they don't die, they downregulate receptors, just like up here. So for some reason, they downregulate CD27. CD27 binds to another molecule, a stimulatory molecule. I forget what it is, CD122 or something like that. CD27, CD122. That's a B cell, so they downregulate CD27. Why do they downregulate IgD to become double negative? They downregulate IgD because they must have gotten a foothold. You know, we know how it is. The B cell receptor looks like this. Here's mu, here's delta, and here's gamma, and so forth. If they downregulate, or they get activated, then they start with this one. They get activated, they move on and switch to this, and then they get activated further as a part of this. I think this is probably the case. Somehow they can splice this out. Now we know that this probably requires activation-induced cytokine deaminase. So somewhere along the process of activation, AICD is out. You know, that's why they call it activation-induced cytokine deaminase. AID must come out and actually, loop out the mu delta region, and so they get gamma. So delta is no longer expressed. CD27 is another interesting problem, because that's downregulated. Why did it pick? Why does it pick CD27? This picks T cells pick CD4 and CD8 because of co-receptors. But why does it pick CD27? Probably because that's an easy molecule to downregulate. And then they switch because of activation-induced cytokine deaminase. Maybe they're switching because delta. You have to think of this way, but why they become double negative. However, there's a whole bunch of just like there's a whole bunch right here, there's a whole bunch of T cells that are double negative, depending on the CD4, CD8, and they get stimulated, downregulated, the autoreactive ones. The autoreactive ones here are also double negative. And I'm predicting there's more than CD27 IgD. There's probably other pathways, other molecules that are downregulated to prevent after chronic stimulation. But these cells are going to be chronically stimulated though. And therefore, they could be chronically stimulated anywhere, and they end up as double negatives. So they could be chronically stimulated in the probably not in the bone marrow, but probably here, over here, in the periphery, in bone marrow, they could have some chronic stimulation. But just like in the thymus, that probably is not, they actually don't get, that's where they're developing. So that's not a good place to downregulate. But in the periphery, for T cells or B cells, or in the post-GC stage, or even in the lymph node or spleen. So I think the thing is what you have to think about is these B cells are chronically activated, senescent, and then they encounter self-reanimation. So that goes into, and there's lots of different kinds. There's like Ipsy was saying, there's the DN2 kind, which is probably naive, closer to DN2, relies on certain cytokines that do that, naive. Or there's memory B cells, but by memory B cells, it must mean they've been stimulated and they take on a memory phenotype. But after enough stimulation, so you think, okay, they're memory, so they're CD27 positive, right? No, because the memory B cells aren't just sitting there memory, there's a maintenance process. We know about this from a long time ago, CD8 memories, maintenance. And how the maintenance occurs, they keep getting stimulated. So, but we know also that's where CD8 T cell senescence comes from. So for B cells, same process. They're going to downregulate something related to this memory T cell. So they downregulate CD27. And of course, they've already switched from delta. So just like Lipsky's paper said, you can get these kinds of double negatives, or you get chronic stimulation double negatives from memory B cells that are kind of along the way. That's why when that paper showed yesterday, there's transitional to naive, and then you get these populations of double negatives that are like double negative, down here, let's just say double negative, DN2 down here after DN1, whatever that is, then DN4 in here, DN4, which by the way, I'll get to this. This is IL4 receptor, and they also produce they respond to IL4 receptor. So, and then there's DN3, which is another population. So, but there's probably lots of DNs that are a result of this kind of chronic stimulation. But probably the DN4, I'm going to say the DN4 might come from this kind of memory response. The DN4 IL4 receptors. Okay, so now let's get the tolerance here. You can have central tolerance, we talked about that's probably mostly deletion, but there's a little bit of energy, but probably not very much. Now, here's the key thing Meffrey said. Meffrey made this point. PTP N22, which is a phosphatase on T cells. In PTP N22 deficient T cells, they have increased activation because they don't have this phosphatase. Interestingly, those, he said, those B cells in PTP N22 macrophage, those B cells have a defect in central tolerance. So so right away you can see, this is the T cell. Now it's on a B cell too, but on a T cell, the T cell is enabling the B cell to survive because it didn't undergo proper tolerance. So you see, you get into this dueling energy thing. The B cell isn't acting on its own here. That's why you end up with all these DN populations. The B cell is sort of trying to go along, and meanwhile getting signals from the T cell, which is surprising because there's T cells in the bone marrow, but maybe down here, maybe this PTP N22. I mean, Meffrey says this will enable a greater escape of central memory B cell, which is surprising, and maybe it acts early in the periphery. But what I'm thinking of is there's a co-evolution. Well, let me get to this. Periphery is a T cell, that's what I'm saying. Periphery, the first step in the periphery, and the second step, even post-UC. Now we get into the problem of the T cell. So And we know that's the case because you know, the DN2, this DN2 requires interferon gamma. This DN4 requires IL4. So it's always there that the T cells have imprinted these cells along with this process. It's easy to understand this process, that the B cells being stimulated by something, and we know what that is. If for DN2 it's DNA, for DN4 it's, you know, worms and things like that. But they're being stimulated, chronically stimulated by these self-antigens. Maybe a worm is, you know, because we know that these CMV can, you know, overstimulate and drive senescence. You know, so maybe in Africa, you know, all the worms are just chronically stimulated, and then the B cell repertoire evolves and the influence is. So it's not really chronic stimulation, but a worm or some infestation can last for a long time, doesn't kill the person. So it could be the worms antigens are driving this. So in the periphery, especially post-periphery, the D and downregulation of a stimulatory molecule to a self-antigen is funny because you think of a worm, well, what's self-antigen about that? You know, the thing is it gets confused. Okay, so you get this chronic stimulation of the B cell, and at the same time, you're getting chronic stimulation of the T cell, you know, like up there. So the T cell's caught up with this. You know, that's something they're looking at. Now, I'm proposing these co-evolve. You know, the chronic stimulation of the B cell occurs in the presence of chronic stimulation of T cells. So the T cells could take on a double negative phenotype. This is the PTPN22 thing. They have trouble being tolerized. But in the absence of defects in a T cell, they could sort of help this B cell. Now, what kind of help does it provide? I guess it depends on what's driving it. What's the chronic stimulation? Or maybe there's something else. Let's just say, for example, for sake of argument, that these B cells have somehow an intrinsic increase in interferon, type 1 interferon. But it's just going to other T cells. But type 1 interferon, this happens to be high in the B cell. So then the TLR7 is high, activation is high. So these B cells are going to be stimulated through the TLR7 pathway, through RNPs, for example, are going to stimulate those T cells. But the same RNPs are now stimulating the B cell, or the T cell, and these are CD4. So the question is, I think that they co-evolve. These T cells are now somehow producing interferon gamma as they co-evolve with this. Whether there is a separate peripheral post-switch pathway at the checkpoint 3 that then does the following thing. You know, that now there's no type 1 interferon, type 1 none, it's not there, it's not high wherever the B cells are made, or they didn't get that signal when they were made. So now the B cells come out, and the B cells are here. Type 1 interferon, or whatever causes it, also the T cells are co-evolving. These are undergoing senescence, you know, and eventually they become double negative. They become specifically double negative 4. So, but they do that in the presence of a T cell that is also responding to self-antigen, and the T cell is now producing, I guess, IL4. It has to, right there next to the B cell, and that causes B cell IL4 receptor upregulated. And the interesting thing is, we know this occurs right here at the peripheral stage, or maybe even this stage, just like the other one. Just like high interferon occurs here. See, PTPN22, lack of this in the T cell affects bone marrow B cells to produce polyclonal autoantigen, you know, and eventually I guess they talk about RA and so forth. So it depends on the antigen that's selected. So the experiment to do is to look at this mechanism. And unfortunately, we can't do central in people, but we can do periphery in different stages of periphery. You know, like transitional T1 and so forth. T1's development, and looking for it in T3, and then looking for this step, chronic stimulation and selection of a BCR here. And I'm going to say this bad thing here because I'm thinking at the same time there's chronic stimulation and selection of a TCR. This is bad because it's a whole bunch of other work. TCR. And just like the BCR, let's say it starts here, just like the BCR, if it gets to here, has downregulated different things. They can downregulate CD27, they can downregulate we know the other ones in the Lipsky talked about. They can downregulate everything and become double negative, but they have different things like sick. He said there's a sick that's high. So they really shows some double negatives have high sick, high signaling, sort of stuck there. This is in the T cell stage. And all of these are going to produce autoantibodies and can produce autoimmune disease. But this is hyperactive inside. So, but they downregulate CD27 to make up for it. So you find all these strange things. In the T cell, for example, the ones that I'm proposing normal humans without the PTPN22 mutation seen in, I guess, RA mostly, but sometimes SLE. Even without that mutation, PTPN22 signaling can have a range. It has a range. It can be high or low. If it's high, the person's in good shape. You got this phosphorus. But if it's low, for whatever reason, some polymorphism, not like the big replacement, but some polymorphism, PTPN22 is sort of low. Well, let me look at this. Sick is high, and that causes double negative. So TCR, you just don't know. Maybe signaling is high, or high because of this, low phosphatase. And then these are more likely to become double negative T cells. And just like I said, they downregulate, they can become double negative, and they can be, and Tregs, right. And then the other thing is the critical role of Tregs, because if you have the Treg deficient mice, and some humans with Treg deficiencies, then this is also amplified. So you got that problem of Tregs not being there. So that's a problem. So TCR, this can help them stimulate through IL-4 or interferon gamma, or it can have Tregs and put Tregs in. So to summarize, not that this is anything new, it shouldn't be new. Autoimmunity is associated with chronic stimulation of T and B cells. Big surprise, right? The autoantigens are always there. They're stimulating the B and T cells. And it's how people handle that. That's true with us and everybody has this. So this will lead to, in most cases, to some level of double negative T cells. The more this chronic stimulation occurs, the more double negative T cells will show up. But the B cells, double negative B and T cells. But the thing is, what occurs leading up to this chronic stimulation? Where the T cell comes from? Are there a lot of CD4s out there? As Meffrey says, chronic the classical DN2 B cell arises because the B cell is being chronically stimulated in an inflammatory environment. What if it's stimulated in a nice tolerogenic environment, like an IL-4 T cell, sitting there, CD4 T cells? Then the B cell will evolve in that environment, and they'll be actually tolerized. We kind of know why, but they won't necessarily be bad T cells, although they may be bad in allergy, because now you got too much allergic response. But this chronic stimulation is the key. Double negative is the key. What kind of double negative is the key? Because depending on the precursor events for the B and the T cell, and that includes signaling problems inside the B and T cell, deficiencies in signaling, or counteracting Tregs. Got to think of Tregs some more. Then that depends on what kind of double negative B cell you will have. And I predict, in every case, if you have double negative B cells developing, you will also, that will that'll leave a mark in that person, and double negative T cells will also develop. So they co-evolve. And they even co-evolve along one of three or, there's 4D and B cells, one of 3 or 4 D and B cell pathways. We know there's several kinds of D and T cells, especially like just CD4 and CD8, but then IL-17 and so forth, interferon gamma. So that's it, So we got to solve that problem.